So before we get started, I wanted to make a couple of things clear about, the final and what we have left. We only have one section left. I don't anticipate that it'll take more than an hour. And just to remind you, basically after that, I don't have anything else concrete planned. So I think I've given a pretty extensive list of things that you can review, many of which are, prior homeworks, quizzes, and tests. So really, I'll after I'm done with that first section, then I'll be turning it over to you. We can talk about any topic, any question you want, even things that I haven't collected yet. Which reminds me, I extended the quiz that was originally due at 5 p.m. today, is now due at midnight. So if you, still need some time to work on that, it's open until the end of the night. If you haven't already seen it, I put an announcement on Canvas, basically I think what's going to be my last set of example problems from the textbook that are good to work on. So definitely take a look at those sometime before tomorrow night. And I know we have such little time left, but I think there's plenty of things you can look at. So before we get there, let's go ahead and hit our last section. So section 4, chapter 10 is all about, we're still in polar coordinates. Now we're going to look at areas and lengths. So yesterday, we spent a big chunk of the day talking about how polar coordinates work. And then we got into a little bit of calculus with them, did some graphing. So now we're going to do areas and arc lengths. So let's get started. So let's just talk about how we do area in Cartesian coordinates. And I'm going to keep this really simple. Let's say that I am looking at this function. So f of x equals 3 over the interval -3 to 3. So really, I am looking at this area here, and I'll just take one representative vertical stripe of this. So really what I'm doing here is this. I'm going to split this rectangle up, and really it could be any curve, but really I'm going to split this curve up into dx wide intervals, and my height for each one of these is just going to be f of x. So if I want to find this area, I'm going to use a Riemann integral, like we always do, to basically chop this up into the infinitely many small, narrow rectangles, and take their areas and add them all together. So I'm integrating f of x dx. So this f of x is my height. This d of x is my width. I'm going to take all those areas, add them all together, and that'll be my final area. So hopefully this looks familiar. We've kind of developed this a few times in the past, which is why I'm going through it relatively quickly. But I think it's good to remind us of the fundamentals of what we're doing before we apply it to polar. Basically, I'm taking a small shape, finding its area, and repeating that process an infinite number of times to get the full area. So that's Cartesian. So let's talk about how we would do that in polar coordinates. So I'm going to do a simple function here. Let's just say the simplest thing I can really do in polar coordinates is something like this. Let's say r equals 4. So r equals 4, hopefully you know why that's this graph here that I'm butchering. But that'll give us a curve like this: a circle centered at the pole with a radius of 4. And now I'm going to draw a representative stripe or a representative element of this circle. So before I do that, I should clear up one thing about the rectangle. With the rectangle, X is my, or in Cartesian, X is my independent variable. And Y is my dependent variable. So really what I'm doing when I take an integral to find area in Cartesian is I'm letting my independent variable, in this case X, vary a little bit. I call that dx. And I multiply that by my Y value, which even if it's not constant, I'm going to assume it's constant. Multiply those together and I get an area. So in this case, we let theta vary by a small amount. And we'll call that d theta. So if I let theta vary by a small amount, we're also going to let r be constant over small interval. So if I do that, let's say, I'll just want to mimic one of these lines here. That'll be my, this right here will be my d theta. So this little change right here is d theta. So if I let theta vary by a little bit, then I get that wedge right there. Or if you want to be geometrically accurate, that's called a sector. A sector really is just basically a slice of a circle. So I have a d theta there, and I have r, which remains constant, which in this case, r is constant because I drew a circle, but r will not always be constant, but that's the way an integral works. We assume over a very small interval that our dependent variable is constant, so we can find that small area. So really, we're finding the area of a sector. So we should probably figure out, if we don't know already, how do we find the area of a sector? So let's start from this. How do you find the area of a complete circle?
Pi r squared.
Pi r squared, right? But I don't want to find the area of a whole circle. I want to find the area of a small part of a circle. So this is the area of a circle. Which means the area of a sector is equal to pi r squared times this ratio. Basically, I'm going to let my theta be some proportion of 2 pi. Basically, 2 pi is one full rotation around the circle. But basically, I want to find the area for any angle. Basically, if I just want a smaller sector of that circle. So if I simplify this, I get pi squared cancels with this pi. So I just get this, the area. Oh, I left the r off here. Pi r squared. So my area of a sector is equal to this, 1/2 r squared theta. I'm guessing this formula right here for the area of a sector is going to look familiar to some of you, but it may be a while since you've seen it. But this area of a sector is exactly where we're going to get our, this is how we're going to integrate to find area. Because you remember, r really is a function of theta. Theta is our independent variable. R is our dependent variable, and they're related through some function. So our area is basically going to be this. If we integrate from a to b, 1/2 times r squared d theta. Or if I want to make this really clearly in function notation, the integral from a to b of 1/2 f of theta squared d theta. So any questions on where this comes from? Just out of curiosity, have people seen this before?
Yeah.
Yeah. I'm guessing from the drawn out, yeah, that it's been a while, but
Theta is radian, right?
it is expressed in radians, yeah. Which is, hopefully that's implied by the fact that I did theta over 2 pi and not theta over 360 degrees.
But you can also take theta by 360, right? It would be the same thing. Like if
it would be, but it's just never done. I'm not going to say that it's impossible, but I don't think I've ever seen polar coordinates expressed in radians. Yeah, I'm pretty confident I've only ever seen it expressed in radians when you're in polar form. And really, thinking back to this class, I don't think we've done anything in terms of degrees. They're really, radians are a more natural way to look at angles. Degrees are kind of a convenient thing, but really most of what you're going to see going forward is going to be in terms of radians when you're dealing with an angle. All right, last call for questions on where this comes from before we make some use of it. All right, so I want to find the area enclosed by one loop of cosine 2 theta. So we could graph this. I will give you a sketch of what this looks like. If you need some practice still at graphing this, and you probably do, we only learned it last night, I would recommend you actually, you know what? There is a technique that I didn't go over yesterday that I really should. So we have this graph cosine 2 theta. Most of what we did last night to graph these, I think the only method we did, and that's my fault, was basically plotting points on a table and then transferring those to a graph. One thing I did not show you was, you can graph these the way that you're used to. And what I mean by that, you can graph them in Cartesian form with theta being on the x-axis, r being on the y-axis. So we have a cosine function here where when theta equals 0, where is this graph going to begin?
One.
It's going to begin at 1, right? And then it's going to go through its normal behavior. So it's going to come back to 1. What is this angle here when this cosine of 2 theta gets all the way back, comes back to its basically completes one cycle? What's that angle going to be?
Pi.
Should be pi. So typically the period of a cosine, if it was just cosine theta, it would take 2 pi radians for that to happen. In this case, I am doubling theta. So basically that means I'm cutting the period in half. Okay, so it takes pi for one cycle to occur, which means this angle is going to be pi over 2. This angle will be pi over 4, 3 pi over 4, and of course starts at 0. So this is Cartesian. And we can transfer that to polar. Basically, what we did last night was we made tables with a few points. And now essentially what I have is, I still have a table, a guide, but it has a lot more points on it. So I am going to draw a dashed circle around the pole. At r equals 1, because really that's as far away from the pole as I'm ever going to get. So from here, I think I can graph this out by the information I have here. So clearly this starts on the positive x-axis. So let's just try to sweep this out the way this happens naturally. So I know that my radius is going to go back to pi over 4, or sorry, when theta equals pi over 4, I'm going to go, basically I'm going to be back at the pole. So pi over 4 is a dashed line like this, diagonal line. So my graph is going to do something like this. So hopefully you agree with that. Basically from theta equals 0 to theta equals pi over 4, this is going to happen like this. So now let's go to, from theta over 4, sorry, from pi over 4 to pi over 2. I know from pi over 4 to pi over 2, I'm eventually going to decrease to -1, but my angle is going to be going from this dashed line to this upward direction. So I believe my graph is going to do something like this from there. I'll go ahead and stop there because that might be a little mysterious why that happens. Any questions on why the graph is being constructed like this so far? Okay, so my next 0 crossing is going to be at 3 pi over 4. So I'll draw that angle in. And even though that's the heading for 3 pi over 4, I'm still negative, so I need to be in the opposite quadrant, which would be quadrant 4. So the graph's going to continue like this. And finally, from 3/4 to pi, I'm going to go back to r equals 1.
Is this cyclic?
It is going to be cyclic. So obviously the way I have it now, it is not, basically the curve is not closed. And what I mean by that is I didn't get back to my starting point. So really what I need to do is, I've only graphed from theta equals 0 to theta equals pi. So to get the rest of this behavior, I really need to do one more rotation. So, or not one more rotation, but I need to graph from pi to 2 pi. But here's the thing, I know that this graph is periodic, so I know that it's going to repeat all those behaviors from pi to 2 pi. So I'm just going to relabel my points here, and that will help me. That will help me finish this graph. So when I go from pi to 5 pi over 4, I know when I get to 5 pi over 4, I'm going to return back to 0. It's gonna look like that. When I go to 3 pi over 2, I'm gonna be negative, so really that's gonna be going upward. And then our last move is gonna be like this. And this graph is called a rose. So any questions so far on how this works? All right, so now I want to find the area. And I want to find the area of only one loop. So what is a good place? Actually, let's go ahead and start the integral. Areas gonna look like this. Integral from a to b of 1/2 r squared d theta. So let's do a smaller version of my Cartesian graph up here. Sine. So 0, pi, 2 pi, pi over 2. No, that's not true. So basically, while I'm drawing this, the question that we need to answer is, what are some good limits of integration in terms of theta to use that'll help me just get one loop of this rose?
Zero to pi over 2.
I think if you do from 0 to pi over 2, you're basically going to get half of one petal of this rose and half of another one. So I would really like to do one closed petal.
Oh, pi over 4 to 3 pi over 4.
Pi over 4 to 3 pi over 4 was probably good because let's go ahead and highlight which one that is here. I believe if you go from pi over 4 to 3 pi over 4, you are going to get this one here. Because as you get to, when you get to pi over 4, r is equal to 0. But as between pi over 4 and 3 pi over 4, the radius is negative. So really you're going to need to be in the third and fourth quadrants. So that's one part of this handle. We said pi over 4 to 3 pi over 4. And I'm integrating 1/2 r squared d theta. So 1/2 of cosine squared 2 theta d theta. So I'll go ahead and stop there and take some questions. Any questions about how I set this integral up? All right, if we're okay with where the integral came from, how do we deal with it?
Wouldn't it just be cos squared theta plus sine? No, minus sine squared theta.
Cosine squared theta minus sine squared theta. Okay, so if this was just cosine of 2 theta, then I would agree, but you know, you have this cosine squared here. So that's actually what makes this a little more difficult to deal with. But I do think you're on the right track of looking at this double angle identity. So let's go ahead and write that down. Cosine of 2 theta equals cosine squared theta minus sine squared theta. Or I'll write the other looks of this as well. 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. So one thing we haven't really talked about, we've used this double angle identity a lot, but we really primarily have used it to transform things in this direction. But we need to remember that we can also go this direction too. So having said that,
Oh, can we do this? If this makes sense.
Okay.
Can I annotate?
yeah, go ahead.
Yeah, okay. So what you can do is sine squared theta equals 1 minus cos 2 theta sine squared theta, or the other way. I'm sorry.
Yeah, cosine squared is the one to go after for sure.
Yeah, I'm sorry.
No, it's okay.
Okay, so that's gonna be 2 squared theta plus 1. So it's half, right? So it's cos squared theta 1 by 4. Just a minute.
Okay.
1 by 4 cos half
There you go.
cos 2 theta plus 1 by 4. So it's just gonna be cos. So if you're gonna convert this in terms of this and that, it's just gonna be half 1 by 4 cos 4 theta.
There you go. And that was the part that I was. So let me go ahead and write that down, then I'll pause a bit and kind of explain where it, or don't really need to explain it. Rios did a pretty good job with that, but let's write this and kind of walk through it again. There are a couple of mysterious things going on that I think are worth calling out. So now this will be 1/4 cosine of 4 theta plus 1/4 e theta. So usually what we've done, and maybe I'm wrong, maybe we have used this to go in both directions now that I'm thinking about it, but really our goal here, or kind of our approach was, I don't have a good way to integrate cosine squared of anything. So I needed to use this double angle identity here. And basically I can solve one of these for cosine squared as Rios did in the annotations there. And that will give me, basically that allows me to trade in my cosine squared for some expression involving just cosine. The only real thing I have to, or the biggest thing I have to be aware of is that I am going to double the angle I started with. So that's why the angle goes from 2 theta to 4 theta. So that part of it, I think that's pretty tricky. So if you have questions, definitely ask why that happened, or yeah, if you have any confusion about what just transpired there, let's definitely talk about it. All right. In that case, this is much simpler to integrate. So the integral of 1/4 cosine 4 theta is going to be 1/16 sine 4 theta plus 1/4 theta. And then once we evaluate at the limits, we are done. So I get 1/16 times the sine of 3 pi plus 1/4 times 3 pi over 4 minus 1/16 times the sine of pi plus 1/4 times pi over 4. And really both sine terms go to 0. So we're just left with 1/4 times 3 pi over 4 minus pi over 4, which should come out to pi over 8. Any questions there? All right, let's go ahead and do one more. So I want to find the area of the region that lies outside of one curve and inside another curve. You're okay, Rita, so I can take care of it.
Yeah, sure.
Okay, so basically I'm trying to find the area bounded by a region. And I have not told you what those bounds are. So the first thing I need to do is define where this region is. So how can I find where this region is? Or what values of theta give this region? If we were doing this in Cartesian and I gave you two equations and I wanted to find the area between them, what would we have to do first?
You gotta equate it, right?
Got to do what, Rios?
You gotta equate it.
Yeah,
Oh.
so first thing I'm gonna do is just set these equal to each other. So I get 3 sine theta equals 1 plus sine theta, which gives me 2 sine theta equals 1. Sine theta equals 1/2, and the first two positive value or first two non-negative values where that happens is pi over 6 and 5 pi over 6. So that's good. We have our bounds for theta. So let's at least start setting up this area. So the area is going to be the integral from pi over 6 to 5 pi over 6 times, I'll just call it r outer. No, it's not even that simple. It should be 1/2 r outer, let's call it RO, squared d theta minus the integral over the same limits of 1/2 r inner squared d theta. So next thing we got to look at is we should probably figure out which one of these curves is the outer curve and which curve is the inner curve. How would we find that out?
You can just plug in an in-between value and see.
Yeah.
which-
So I was going to try to draw basically a picture of what's going on here. So the first R value is a circle that touches the origin and has a radius of Yeah, it should be a radius of 3. Yeah, radius of 3. Actually, sorry, diameter of 3. And then this other one is, this is the cardioid that we've looked at before. Maybe not to scale, but kind of help us get our bearings. So basically, I'm looking for the area that lies inside the circle, but outside the cardioid. So we're going to find this guy here. So let's say that you didn't, you can definitely find that out without using the graph. If we choose a point somewhere on our interval. So we're looking at, our interval goes from pi over 6 to 5 pi over 6. So what happens if I choose pi, which is directly in between? Then I get 3 sine of pi equals 0, and 1 plus sine pi equals 1. Pi is not between them. Pi over 2 is. So 3 sine pi over 2 is 3, and 1 plus sine pi over 2 is 2. So that means that my outer function is the circle, and the inner function is the cardioid. So now I can rewrite my integral to like this. The integral from pi over 6 to 5 pi over 6 of 1/2 times 9 sine squared theta theta minus the integral from pi over 6 to 5 pi over 6 of, I'll just leave that one for now because it's going to be a little more involved. 1 plus sine squared, or sine theta squared d theta. Go ahead and stop there. Any questions on the setup of that integral so far?
Wait, why does it equaling 3 and 2, why does that mean it's the circle is the outer?
So I want to find the area of the region inside. So the circle is this first equation. So circle, and this one is a cardioid. And basically I'm saying, think about the way we've done this with Cartesian. The outer curve is the one that's further from the x-axis. But we're in polar, so I want the curve that's farther away from the pole, farther away from the origin.
Oh, that makes sense.
Okay, good. All right, so good question. Anything, are we okay with the setup here? All right, one thing I can do, and maybe some of you noticed that this was possible or wondered if it was possible. I can bring these together into a common integral. So I'll go ahead and do that now. So I have 9/2 sine squared theta minus 1/2, and now I'll go ahead and square this. 1 plus 2 sine theta plus sine squared theta all of this d theta. Can anything simplify here or not really? So 4 sine squared theta plus sine theta minus 1/2 d theta. So I'm gonna go ahead and leave it there. I would definitely encourage, if one of the things you need to work on is using trig identities to make to facilitate integrals, to make integrals possible, I would definitely come back and practice this. But for now, I'd like to focus on setting these up. So you can definitely complete this. And to that end, why don't I ask for it here? What, based on what's here, what trig identity should I use to help me simplify that integral? So the only part of this that's going to be difficult to integrate directly is the sine squared. So for this, I suggest looking at your double angle identities. All right, any more questions on that example? All right, so our next thing here is finding points of intersection. So I want to find all the points of intersection between these two curves. So r equals cosine theta and r equals 1/2. So what should I do first? So just like last time, if I want to find where two curves intersect, I'm going to set them equal to each other. So I'll start with this cosine of 2 theta is equal to 1/2. So from here, we got to be really careful about how we solve this because, or yeah, how we handle this, because there are going to be lots of intersection points between these two curves, because cosine is a periodic function. So hopefully we just saw from the rows that, you know, even though this cosine function has a period of pi, if we're trying to graph this, letting theta go from 0 to pi didn't give us the full curve. We still need to let theta vary from 0 to 2 pi to get the full behavior. So we really need to find all the angles theta on that interval 0 to 2 pi that'll give us that are going to give us an intersection here. So let's do this. I know 2 theta is going to be equal to, just algebraically, the inverse cosine of 1/2. So instead of just listing the first angle, I want to figure out all the angles where that's going to happen. So what angles have a cosine of 1/2?
$15.
15.
I'm sorry. I was thinking about cos 60. So that's
Yeah,
30.
so yeah, but we want that in radians. So basically, yeah, 60 degrees has a cosine of 1/2, but for now, I'll list that in radians, pi/3. So just a reminder here. What two quadrants is cosine positive in? So remember the cosine of an angle really just gives you its x coordinate. So because of that, the x is positive in the first and the fourth quadrant. So one angle I'm going to get that from is pi over 3. But I'm also going to get it from the same reference angle in this quadrant. So that'll be 2 pi minus pi over 3, or 5 pi over 3. Any questions on how I got those two angles so far? So I've definitely found two angles, but remember, I'm going to divide these by 2. And I want to find all my angles between 0 and 2 pi. So I'm going to go a little further to make sure that I'm going to be complete. So if I go around the circle one time, basically I'm going to find two more angles here, 2 pi plus pi over 3 and 2 pi plus 5 pi over 3. So now I have this list: pi over 3, 5 pi over 3, 7 pi over 3, and 11 pi over 3. And my last step here is going to be to solve for theta. So cutting all these in half is going to give me pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we're pretty much there. We just need to write down what points we get from all those. We get 1/2 pi over 6, 1/2 5 pi over 6, 1/2 7 pi over 6, and 1/2 11 pi over 6. Any question about that? All right. All right, similar thing here. I want to find all the points of intersection. So first thing I'm going to do is to set these equal to each other. So I get 1 plus cosine theta equals 1 minus sine theta. And from there, I get negative sine theta equals cosine theta. All right, so how can I continue from here, solving this equation for theta?
Would you be able to divide each side by cosine theta and make it tangent theta equals 1, or negative tangent theta?
Yeah, that's a good idea. So I can definitely do that. And that gives me negative tangent theta equals 1, which I'll slightly modify to tangent theta equals negative 1. All right, so where does that happen? Where's the tangent of theta going to be equal to negative 1? And what values of theta? So just to refresh, remember that tangent, the definition of tangent is sine, the ratio of sine to cosine, sine divided by cosine. So remember that the sine of an angle basically gives you its y coordinate on the unit circle. The cosine basically gives you what the x coordinate is on the unit circle. And the tangent gives you the sine divided by the cosine. The only way for the sine divided by the cosine to be negative is if x and y have different signs. One is positive, the other is negative. So in quadrant 1, x is positive and y is positive. So that means the tangent is going to be positive there. In quadrant 3, you have x is negative and y is negative. So that means the tangent is going to be positive. Negative divided by negative is positive. So tangent is going to be negative in quadrant 2 and quadrant 4. Because x is negative and y is positive. And then in quadrant 4, the opposite is true. X is positive, y is negative. So my angles are going to be 3 pi over 4 and 7 pi over 4. Any questions on how I got that? Right, and the radii that goes with those are so sine of 3 pi over 4 is radical 2 over 2. So 2 minus radical 2 over 2. 3 pi over 4. And I believe it's radical 2 minus 2 over 2. 7 pi over 4. Any questions there? All right, last thing I got for you is arc length. So a couple of questions to kind of bring us back up to speed for polar curves. So when we're finding arc length in Cartesian coordinates, we're integrating from A to B. What are we integrating to find arc length in Cartesian coordinates?
Theta.
Just theta? Oh, Cartesian is like rectangular x and y. So hopefully this looks familiar by when I write it down. So this is typically what we've done in Cartesian coordinates. So for parametric curves, what modification did we make? I mean, obviously it was similar, but and we did this last night, right? So what did this integral look like for a parametric curve?
Isn't it dx over dt squared plus dy over dt squared?
Yep. Yes, which is basically not a coincidence that this looks like the Pythagorean theorem. So really, we're getting the parameter involved here. we're taking the derivative of x with respect to t, the derivative of y with respect to t, squaring them both, taking the square root. Basically, that's how I'm getting my little tiny arc lengths, is through Pythagorean theorem. I can really do the same thing with arc length in polar form. So for parametric, your arc length is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared with respect to t. But really, so t is the parameter for parametric. In polar, we can do the same thing. So really, this is going to look almost exactly the same as what we do for parametric, except my parameter is going to be theta. So dx d theta squared plus dy d theta squared d theta. So I can find the arc length of a polar curve using this approach. And the two pieces I need are dx d theta and dy d theta. So a little, basically, when we did this last night, we were talking about tangents. So given that r equals 1 plus sine theta, how can I work toward figuring out dx d theta? We'll start with that.
Would we use the r sine theta?
Yeah. So first thing we need to do is we don't have x right now, so we need to make an expression for x, and we know that x equals r sine theta. So specifically for us, that'll be 1 plus sine theta, and this should be cosine. Got him confused. So 1 plus sine theta cosine theta. So now that I have x in terms of theta, I can definitely find dx d theta. I'll go product rule. So this will be cosine theta times cosine theta plus 1 plus sine theta times negative sine theta. Simplifies to cosine squared theta minus sine squared theta minus sine theta. So we're good on dx d theta. We got one of our pieces. Now we need the other one. Y equals r sine theta. So we'll get 1 plus sine theta sine theta. And we can take our derivative the same way, using product rule. So this will be cosine theta sine theta plus 1 plus sine theta cosine theta. So I get 2 sine theta cosine theta plus cosine theta. So I could put these under the integral and start working with them. But can we rewrite either one of these a little more simply? So think about that while I start setting up this integral. Then any trig identities we could apply here,
For which one?
either for both of them.
Oh yeah, that's just one of them is cos theta, the other one is sine theta.
Yep, so this right here is cosine 2 theta. And this one here is sine 2 theta. So hopefully that makes this a little simpler to deal with. So dy d theta, or I guess it doesn't matter what we're going to do. So I get cosine 2 theta minus sine theta squared plus sine 2 theta plus cosine theta squared d theta. If you have in your notes from yesterday what the cardioid looks like, I need the full interval 0 to 2 pi to get the full length of it. It's a closed curve. It basically loops back on itself. So let's expand these now and hopefully some things simplify for us. So I get cosine squared 2 theta minus 2 sine theta cosine 2 theta plus sine squared theta plus sine squared 2 theta plus 2 sine 2 theta cosine theta plus cosine squared theta d theta. So we got a few things that simplified there. I definitely have Pythagorean identity a couple of times. I have cosine squared 2 theta plus sine squared 2 theta. I have sine squared theta plus cosine squared theta. So I should have 2 plus 2 sine 2 theta cosine theta minus 2 sine theta cosine 2 theta. And for our purposes, I'm happy to leave it there. It's a pretty complicated integral to do by hand, and I'm really a lot more interested in getting to the setup. Any questions about how we did that before we do our last thing? All right, one more. So I want to find the length of one loop of the spiral. So r equals theta squared. So what should I do first?
Find x and y.
Okay, very good. So what's x equal to?
R cosine theta.
X equals r cosine theta, which means that x is equal to theta squared cosine theta. So let's just handle that derivative first. So product rule gives me 2 theta cosine theta minus theta squared sine theta. I'm gonna put these side by side, they're pretty short. Y is equal to r sine theta, which is equal to theta squared sine theta. And dy d theta equals 2 theta sine theta plus theta squared cosine theta. All right, so I got dx d theta, dy d theta. So now I can set up this integral from 0 to 2 pi. Of 2 theta cosine theta minus theta squared sine theta squared plus 2 theta sine theta plus theta squared cosine theta squared d theta. If memory serves, we get a few favors in terms of simplifying here. So I get 4 theta squared cosine squared theta minus 2 theta cubed sine theta cosine theta plus theta to the 4th sine squared theta.
Shouldn't it be just theta cube sine?
Actually, it should be 4 times that.
Oh yeah, 280. Yeah.
Yeah, it should be 4 times that. I think everything else looks okay. All right, for the second bracket, I get plus 4 theta squared sine squared theta plus 4 theta cubed sine theta cosine theta plus theta to the 4th cosine squared theta d theta. Do we see anything getting more convenient? I see 4 theta squared cosine squared theta and a 4 theta squared sine squared theta. So that tells me I have 4 theta squared. Anything else work out like that? Yep. I got theta to the 4th sine squared theta, theta to the 4th cosine squared theta. And yeah, I was right. So in that just totally unite with each other. So from here, can I do anything else? I can factor out a theta squared. So I get theta times 4 plus theta squared d theta. Is there some way we can integrate this? There's a technique we've done this year, probably early in the year, that will help us do this integral.
Integration by part.
By parts, I don't think that'll help, but let's try a U substitution. So if U is equal to 4 plus theta squared, that means du is equal to 2 theta d theta, which means theta d theta is equal to a half du. So let's also transform the limits. U equals 4 plus 2 pi squared equals 4 plus 4 pi squared. And our other limit will be 4 plus 0 squared. So this integral should look like this now. from 4 to 4 plus 4 pi squared of 1/2 times u to the 1/2 du. And then from there, we can just handle it normally. So this comes out to be 1/3 times u to the 3/2 of and I believe 1/3 time, I think, yeah, 4 to the 3/2 is just 8, so minus 8/3. Any questions on this one? All right, that is all for that's basically the class. So I'm gonna go ahead and close this out and save it. So like I promised you, basically the rest of this time is, I will talk about whatever you all want to talk about. So you know better than I do what things need to work on. So we'll go from there. Let's take a short break. So let's come back at 7:34. And then, yeah, come back with questions, and yeah, basically we can spend the rest of today and the first part of tomorrow reviewing the things that are important for you all to review. So I'll see you all in about 11 minutes. All right, everybody, I am back, so I'll go ahead and open the floor up to all of you. Is there anything? Yeah, what would you like to talk about?
Can we go over finding the sum of a series?
Yeah, any particular kind of series?
No, not exactly.
Okay, so I really, and I think I've said this before, but I'll go ahead and say it again. Most types of series, we don't have the tools to find sums of. There are really only a couple kinds of series that I have talked about where you might be able to find a sum. Do you remember what those are?
Can you do some alternating ones?
So even most alternating series don't have weapons, like we don't have the tools to find the sum, even if they converge. So really, the only two types of series we've talked about where we can find sums are geometric and telescoping. So let me see if I can hunt down some examples. And I'm pretty sure I can come up with some examples of geometric series off the top of my head, but it's a little harder.
How about 1/n+1 and 1/n+1 times n+2 for telescoping?
Sure. All right, so here's what we can talk about. So first of all, does this converge?
Yes,
How do you know?
order of the system.
So you could do either a limited comparison or a direct comparison with an appropriate P series, but yeah, this thing converges. And I believe we can find a sum here. So how would we go about doing that?
I'm assuming you start off with partial sums.
Yeah, so where do I go from here then?
So would it be a over n+1 and then b over n+2?
Yeah, okay. So you said partial sums, but yeah, I wanted to make sure you meant partial fractions. So good. So if I clear the denominators, I'm just gonna leave off the sigmas for now. So I have 1 equals a times n+2 plus b times n+1. All right. Can we get the values for a and b?
Wouldn't you set n equal to 2
I don't think 2 would help.
or -2?
-2 is good. So if n equals -2, then I get 1 equals, first term vanishes, b times -1. So b equals -1. That's good. What other value of n is good to use?
-1.
-1 equals, sorry, that implies that 1 equals a times 1. That's easy enough. All right, so now we can look at this series like this. From 1 to infinity of this sum, 1 over n plus 1 minus 1 over n plus 2. Okay. So we've re-expressed our sequence. Where can I go from there?
Can't you do them separately or no?
What do you mean by that?
Do the series 1 over n plus 1 minus the series of 1 over n plus 2.
You can. I recommend keeping them together because if you pull them apart, it's going to be really hard to see how the series behaves. Also, if you pull them apart, neither one will converge on its own. Do you see why? Like, for example, if you just look at this series, that diverges. Because of, you can compare it to the harmonic series 1 over n. But that will diverge. So we really do need to keep them together. Not just for convenience, but this is the only way we're going to get it to converge. So any other suggestions for where to go from here? So what we're looking at a series, we don't really understand where to go. What's a good thing we can do to just get a sense of how it works? What can we start doing?
Can you do limit comparison?
Limit comparison is only going to tell us, so those tests, that test only really tells you if a series converges or diverges. And we know it converges already. We're looking for a sum. So let's just start by writing out some terms. So if n equals 1, I get 1/2 minus 1/3. When n equals 2, I get 1/3 minus 1/4. What do we notice as I'm writing these terms out?
Everything cancels except the first term.
Everything's going to cancel except the first term. So let me just, for some generic n,
There should be a limiting value, right?
yeah. And that's why I'm writing out so many terms. So hopefully you're noticing this happens, you know, these internal terms will all get canceled out. So really what I'm left with is, you know, this sum is going to be equal to 1/2, or the limit as n approaches infinity of 1/2 minus 1 over n plus 3. Because you said the more, if I just keep on listing terms, all that's going to survive is the first term and the last term. So because of that, the sum is going to be 1/2. Any questions on that? Any questions here? All right, so that's a good example of a telescoping series. What else do you all want to talk about?
Do you know what was generally missed a lot on the first test?
I don't remember, but I can go take a look. Let me stop sharing. That was quite a while ago. Go ahead and share it just in case it jogs anybody's memory about what they want to look at.
Area between curves. Yeah, that's hard.
Okay. So there's one on the short answer portion. Did I do one that was a little more involved? That's volume. I did not. So let me see if I can hunt down an example of that. Those are pretty easy to find.
Also the work, the work, especially the one that we just saw right now in the exam.
Yeah.
The first exam, like the one with the pyramid. Yeah, that one.
Okay.
That's like so hard.
All right, I can go over that one.
Now. Three. 4. 5.
I'm gonna write the functions down in chat just because I can't share my screen and look at them at the same time. All right, so I want to find the area bound. So what are my bounds? Y equals x times e to the negative x squared. Y equals x plus 1. X equals 2 and y-axis. All right, so I want to find the area of the region bounded by all 4 of these objects. So how do I set that up?
plot it.
Okay.
If that, I don't know.
So I could definitely plot the straight lines. So I care about, so really x equals 0 and x equals 2 are my left and right boundary. X plus 1, this is not going to be to scale at all, but that's fine. So there is y equals x plus 1.
We got it.
All right, so do we know what the top curve looks like? Y equals x times e to the negative x squared. So this is one of those times, I mean, if you can readily plot a curve, it might be a good thing to do. I don't think in this case you necessarily can. I don't off the top of my head know what that curve looks like. So is there anything else I can do to help me?
Oh, when x is 0, y is 0. That's true.
When x is 0, y is 0, so that's true.
So when x is 1, y is 1 over e.
Okay, so 1 over e is, so this is helpful. I mean, I really don't need to get this thing, and I don't really need to have the shape of this really ironed out, but you know, it starts off looking like this. What information, so of the things I've plotted for, what valuable information does this give me?
It tells you which one's the top function.
Yeah, exactly. And that's really all I care about. And I believe this probably trends back down, but I think that's what happens, but I don't really, that doesn't need to be true. All I really need to be true, I figured out, or you figured out what basically what the greater and lesser functions are, which is important. So from here, how would I continue finding this area?
You're doing this without graphing it. Would you just like plug in 1 and see which gives you a greater value?
Yeah, absolutely.
All right.
Yeah, and you could do that. So if x equals 1, then you get y equals 1 over e, 1 over e, y1, and then y2 is equal to 2. Oh, I messed up here. Erase my mistake because I don't know really how to fix it. But yeah, so that's enough to, yeah, that gives you what the upper function is and what the lower function is. And you can do that without graphing. So now how should I continue?
The greater minus lower, and it times dx times integral.
Okay, well, not times the integral, taking the integral of, so yeah, the integral from a to b of function upper minus function lower dx. What are my limits of integration?
0 to 2.
0 to 2. So I'm using x as my independent variable, so I need to have x limits my integral. The upper function is x plus 1. The lower function is e to the negative x times e to the negative x squared dx. All right, so we got the integral set up. So how do we integrate it now?
You can just take x square equals u. That works.
Take what?
Okay, you could just split it up. Like you could just split everything up.
Okay, I'm gonna leave these two together because they're pretty easily to handle.
And then you can go either integration by parts or u, or substitution method.
I'm gonna go substitution. I don't actually think integration by parts will work.
Yeah,
Um,
yeah, it won't work. It won't work.
Yeah, so if you do integration by parts, that means you're gonna have to integrate either. Yeah, I mean, I think you would definitely want to differentiate x, which means you would have to integrate e to the negative x squared, which can't be done. All right, so u, what did you say you wanted u to be equal to?
Negative of x squared or x squared.
Let's do negative x squared. They would both work. So that means du is equal to negative 2x dx. All right, so keep on driving. Where do I go from here?
You would plug 0 and 2 into u
Yep, so
or for
u,
x.
u equals negative 2 squared equals negative 4, and u equals negative 0 squared. All right, so now I'm integrating from 0 to negative 4. Okay, so now I can start transforming this integral. So the integral from 0 to negative 4 of what? Tell me how to handle this from here.
There will be a plus 1/2 outside and e raised to u du.
Plus 1/2 outside. So I think I know where you're going with this. I am going to I'm just going to pull out a negative 1/2 for now because I think you'll see why. I know what you're getting at, but I'm going to keep it as negative 1/2. So negative 1/2 e to the u, or the integral of e to the u du. So because of that, yeah, now we could, this integral is pretty easy because e to the u is its own integral. So I get negative 1/2 times e to the u from negative 4, or 0 to negative 4. So I get negative 1/2 e to the negative 4 plus 1/2. So yeah, 1/2 minus 1 over 2 e to the 4th. Okay. So we're kind of doing this in a weird way, but that's okay. Now what I have for my area is this, the integral from 0 to 2 of x plus 1 dx minus this thing I just found. So minus 1/2 minus 1 over 2 e to the 4th. All right, so got the more complicated of the two integrals done. Now what?
That would become 1/2 x squared plus x from 0 to 2.
Yep. So this comes out to be 1/2 of 4, which is 2, plus 2. And that's it. That comes out to 4, plus 1/2 e to the 4th, minus 1/2. So final answer is 3/2 plus 1/2 e to the 4th. Any questions about that one? All right, good question. What else?
Exam 1, the word question.
Oh yeah, you mentioned that. Okay. Let me actually share my screen because I'm just gonna go over the solutions that I wrote for that one. I think they're pretty detailed. Okay, so I have a tank in the shape of a pyramid, square base pyramid, full of water, and I want to pump all the water out of the top of it. So that is what, 2C? So really I did this in steps. So first thing I did here, and I'll try to mimic this drawing on this pyramid here. Basically, I'm gonna take a representative kind of a slab, a slice of this water in this pyramid. So that'll be a square slice. And I'll let this thickness be dy. So basically, y is going to be my independent variable because I want to integrate, not only that little slice of the water in there, but every slice of the water in there from the bottom to the top of that pyramid. And I think it is logical to do this in steps. So the first thing I did was the volume. So I want to find the volume of that slice of water. So the volume is going to be equal to, basically it's a rectangular prism. It's a square with some thickness. I do not know what the length of that, or what the side length of that square is, but I do know it's a square. So for now, I'm just going to call that L squared times dy. If you look at my solution on the right here, I know that since my pyramid has straight sides, then basically as I go from the bottom of the pyramid to the top, the side length of that square will decrease linearly. So I just have this small table here with 2 points in it to help me figure out an equation for the side length in terms of y. So I know that when I'm at the bottom of the pyramid, the side length is going to be 4, because that's exactly how big the base is. And I know that at the top of the pyramid, when y is equal to 8, my length will be 0. So basically, I use those 2 points to help me come up with a linear equation for L in terms of y. So that allowed me to do this. I know that volume as a function of y is equal to 4 minus 1/2 y squared dy. You okay with me? Are you okay with that so far?
Why is it 1/2?
I'll go ahead and just, I'll develop this equation here. So basically what I'm doing is I'm trying to find y equals mx plus b. And really, I need to rewrite that. So really, I'm doing this. L equals my plus b. Because y is my independent variable, L is my dependent variable. So I'm trying to write this equation that relates the length of the side of that square to my height from the bottom of the base. So first thing I want to do is find the slope. So my slope is going to be equal to L2 minus L1 over Y2 minus Y1. So 0 minus 8 over 4 minus 0. So that gives me negative 8 over 4, which is negative 2. Oh, now, did I do this wrong the whole time? Nope, I did it wrong just now. Value's in the wrong place. So 4 minus 0 over 0 minus 8, that comes out to negative 1/2. So now I know I have L equals negative 1/2 y plus b. And I kind of can get for free that b equals 4, because I know if I plug in 0 for y, I'll get L equals 4. So that's how I get negative 1/2 y plus 4. You okay with that?
Yeah, that makes sense.
Good. So I have a volume function. I know the volume of any slab of water as a function of y. So the next step I want to take on top of that is the mass. And I will direct your attention to this, the density of water. So density is equal to mass divided by volume. Which means that mass is equal to density times volume. So if you realize that, then it's really easy to get from volume to mass. I just take my volume function and multiply it by 1,000. So then I get 1,000 times 4 minus 1/2 y squared dy. The next thing I need to do is, and maybe I should remind you of the finish line here. Work is equal to force times distance, right? So basically that's what I'm building up to. I can start with the volume. And then from volume of water, I can get the mass of the water. Now that I have the mass of the water, I can get the weight of the water. So one thing we know about the weight of an object, and we're doing this whole thing in metric, is the acceleration of gravity on this planet is negative 9.81 meters per second squared. And I think we were just using 9.8 actually. So negative 9.8 meters per second squared. So because of that, I can say that the weight of that water is equal to 9.8 times 1,000 times 4 minus 1/2 y squared times dy. So I get this weight is equal to 9,800 times 4 minus 1/2 y squared dy. All right. Any questions about any step of that process so far? All right, so now that I have my force, I am ready to find the work. And remember, I'm trying to pump this water out of the top of the tank. So I'm going to integrate. I want to pump out all the water. So I'm going to integrate from 0 to 8 over the full height. I'm going to integrate my work function 9,800 times, or this is my force function, I'm sorry, 4 minus 1/2 y squared. So from there, remember, so the thing I just erased, work is equal to force times distance. So this slab of water that I've drawn, I need to pump it up to the top. And remember, the lower the slab of water is, the further it has to be pumped. And exactly what is that distance that I'm going to move this water? Basically, it's equal to this, 8 minus y. Because if I'm moving it from the bottom, where y equals 0, I'll have to move it 8 meters. If I'm moving the water from the top, at the top, the value of y is 8 meters, so I'm not moving it anywhere. So that distance is going to be 0. So basically, this right here is my force, the weight of the water, depending on what the value of y is. And really what this dy is part of that. Because remember that dy, the place where we originated that is my that's the thickness of that slice of the water that I'm looking at. And then the 8 minus y, that is my distance. So I think that was, no, I don't think that was the trickiest one in the test. So any questions about that one? Okay. Right, what else do we want to talk about?
That's it for me.
Okay.
Professor, may I leave? I want to revise something else, like some other questions.
Yeah, sure. I mean, this time really is for you. So if you're good to review on your own, that's fine with me. I'm here for whatever you all need.
Let me just check last minute.
Okay.
Oh yeah, I forgot the whole the approximation, the integrals. That's a bit hard for me. All three of those.
Oh, the Taylor's inequality?
No, not that. That's okay. The other one, the Simpsons.
Oh yeah, so remember, so I think I thought I said this, but I'm not going to test you over Simpson's rule.
Oh, sorry. The other one, the right end, the left end, and the midpoint and trapezium.
Okay, so yeah, we can do one of those. You have a specific example in mind?
E raised to x.
E raised to the x? That's fine. I mean, yeah, that's totally okay. So that's one we can integrate exactly. So that's a good one. So because we can check ourselves. So let's do this. Let's integrate So let's have f of x equals e to the x. I want to find the integral of f of x dx. Let's say from 0 to 4. And pick a method. Which method do we want to use?
Left hand?
Yeah, let's do the left-hand approach. So we want to use the left-hand approach, and I'm going to say using 4 intervals. Okay, so where do we go from here?
B minus a by n.
Okay. And what is this giving you?
The width of each segment.
So we have 4 intervals. They're all 1 unit wide. So that's good. So this is the width of each sub-interval. Okay, so what do we do with that?
Wouldn't it just be the f at the midpoint? Oh, sorry. What am I even on about? The I don't.
So one thing I recommend, and you don't have to know exactly what this curve looks like, but I know it's an exponential function, so it should look something like this. So 0, 1, 2, 3, 4. So basically, I'm using the left-hand approach. So my rectangles are going to look like this. Remember, when I use these left-hand or midpoints or right-hand approach, I'm finding the areas of a few rectangles and then adding them together. So hopefully this makes it a little more clear what we want to do. So now how would I find the areas of these 4 rectangles that I just drew?
Wouldn't it just be f of n plus 1 times 1? That I'm sorry, like you have f of 0, and then f of 0 times 1, and then f of 2 times 1, and f of 3 times 1, and f of.
So here's what I heard. I'm sorry if I missed you or you cut out or anything, but I only see 3 areas so far.
And then f of 4 times 1.
Not f of 4. So remember, you're using left-hand approach, right?
Oh, yeah.
So your sub-intervals are going to be from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So the left-hand approaches are going to come, the left end of each interval is going to be 0, 1, 2, and 3. So I'll shoehorn in here. is I want f of 1 times 0 as well. So my area is going to be f of 0 times 1, which is going to be 1 times 1, plus f of 1 times 1, which will be e times 1. Then e squared times 1, then e to the e cubed plus 1. Which comes out to be I got approximately 31.19. Do you think that estimate's going to be too large or too small?
It's too small, right?
It's going to be too small. So let's make sure that let's see if we're even close. So we can find this integral exactly. So what is e to the 4th power? So this comes out to be approximately 53.60. So our approximation is not very good, but we're using intervals that are pretty long and pretty wide. But like we predicted, we did have an underestimate, and it's pretty severe.
But I think it would be more better if you take the midpoint, right?
Probably. Let's not go through the midpoint, but let's at least do this. If I want the midpoint approach, then what values of the function do I need to sample at?
Whatever that f of that over 2. Oh, no.
I'm not sure I followed. So yeah, what x values do I need to plug into the function?
The top minus the bottom by 2.
That's not how you find midpoint. You add them together.
Oh yeah. Top.
But yeah, so yeah, it's going to be f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5. So yeah, I mean, you can calculate that if you want to see if it gets any closer, but it's probably still going to be pretty wrong, just because of how wide our subintervals are.
Thank you, Professor.
Thank you.
Yeah, that's it for me.
Okay.
Yeah.
All right, what's next?
Can we go over some trig identity problems?
Yeah. Let's see if I can find some examples. So how about this one? Let's do the integral of sine to the 5th of x dx. So how should we attack this one?
I know one of the like big goals is to add in like cosine in there.
Yeah,
like not just
so,
all sine.
and why is that? Why do we want to have a cosine in there?
Um, so that we can start. I'm not sure.
So really, we're trying to get to a place where we can make U substitution happen.
Oh, okay, yeah.
So right now, what we have is we have U equals. I mean, a natural choice for U would be sine of X because, you know, we can kind of see as a composite function happening here where the inside function is sine of X, outside function is X to the fifth, and you compose those together and you get sine to the fifth of X. So if U is equal to sine of X, that's great, except I don't have a D, like the du that would go along with that is cosine of X dx. So I need to get to, you know, maybe it's not going to be exactly this, but I need to get to a place like this where I have, like, basically I'm trying to set this up for U substitution. So what can I do to get me on that path?
Can you turn sine squared into 1 minus cosine?
Yep, I can definitely do
Squared.
that. So that leaves me with sine cubed of X. And then I have 1 minus cosine squared of X dx. So have I gotten to my goal yet?
No, because cosine's squared.
So what should I do now?
Would you distribute? No.
No, that's not gonna get me there. So I'll go ahead and I'll take over for one more move. I'm gonna do this. I'm gonna take away one, or not take away, but I'm gonna convert one more. So basically I took another sine squared and I rewrote it as 1 minus cosine squared. So now I have this. So I'm gonna go ahead and distribute and move it to the front. So this becomes 1 minus 2 cosine squared of X plus cosine to the fourth of X times sine of X dx. Do we notice anything now?
Isn't 1 minus 2 cosine squared x an identity?
It is, but I don't think it'll help. So keep in mind, our goal was to try to set up something involving U substitution. Can I do that now?
You could substitute the sine x for u.
If you go that direction, then you're going to have basically U times 1 minus 2 du squared plus du to the fourth. That's not the direction we want to go. So I think we thought we were going this way. It didn't end up working out. But this isn't a form now where we can do U substitution.
Oh, would you do cosine?
Yeah, that
U
should work.
equals cosine.
So if U equals cosine X, what does du equal?
Negative sine x.
Your sine X dx. So if we do that, then this becomes like this: 1 minus 2u squared plus u to the fourth times negative du. So is this an integral we can handle?
Yeah,
So and really, it all kind of comes down to, you know, Pythagorean identity in this case. Basically, you can take a sine squared and re-express it in terms of cosine squared or vice versa. But you're kind of limited. I mean, it's powerful, but you're really only limited to, you know, you can only do that with powers of 2. So really what you have here is you're going to be stuck with the sine of x. There is no way to fully write this thing in terms of cosines.
isn't there like a, not a rule, but like a common theme where if it's odd, if like the power is odd, you can do this or something?
Yeah, and that's exactly what. Yeah, so it's what I was trying not to say that explicitly, trying to have you discover it. But yeah, the fact that you have an odd power of sine, that's what kind of gets you to, all right, that's going to eventually be my du or something involving sine.
So if it's even, how would you go about it? Or is that not
It's-
gonna be a
If it's
question?
sine or cosine, it doesn't really resolve itself easily
Okay,
because yeah, you really need, so you need to get to a place where you can involve u substitution, and it's not completely true, but in a way you can see, you can kind of look at sine and cosine being each other's derivative because they're really only different by that negative sign.
okay.
But that only applies for sine to the first power and cosine to the first power. So yeah, if I just give you like sine to the 4th of x, that yeah, we would need to handle it a different way.
Okay.
All right, so you want to keep going, or I mean, once you get it here, I think you can integrate things like this, but we can finish it if you want.
No, I understand from there.
So what I recommend is I'm going to just copy the link where I got this, because there's a bunch of examples on here, and some of them are not relevant to what we did. Like for example, we did not do anything with the sum and difference identities, but I still think this is a good source. So, and really for anybody who's Googled like examples of really lots of kinds of problems, this math.lamar.edu probably shows up a lot. They have a lot of good examples that are good to look at, both worked and unworked ones.
Does that same kind of idea of the odd ones work for like tangent and secant?
Yeah, that's why I posted that link, is because
I was
yeah, the
looking at
odd,
example 8.
yeah, so I'm looking at 5, 6, 7, and 8, all kind of they're all useful to just show all, basically all the different versions of that might happen.
Does cosecant not really show up on those kind of problems?
I mean, it can. It really doesn't behave any differently from secant square, right? Like if you look at the Pythagorean identity that involves cotangent and cosecant, really they're going to behave exactly the same way.
All right, that makes sense. So on exam 1, we were allowed to do whatever like shell or disk method for each one. Is it gonna be similar to that on the final?
Yeah, I mean, you should definitely be ready for a volume to show up. Yeah, and yeah, definitely be aware of how each method works. So like I'm looking at exam 1. That example I gave you, that's pretty easy to set up using the disk washer method or the shell method. Not every region lends itself to both. Sometimes one is far easier than the other. Sometimes one of them is just not possible. But yeah, this one I specified it. Use this method. Use this method. If I don't do that, then if I don't specify a method, then you're welcome to do whatever makes more sense.
Okay. How's tomorrow gonna work?
Pretty similar to the way it worked the first 2 tests. The final is going to be a bit longer than the other 2 tests. So I think we're going to start at around 7:30, closer to 7:30 than 7:40. Otherwise, it's going to be pretty similar format to the first 2.
So should we just bring questions and stuff?
Yeah, so yeah, the first part of class is gonna be, yeah, just kind of like free form review, kind of like this has been, and the first half of the other 2 test days has been.
Okay.
Hey, Chris, do you need anything?
No, I don't. Thank you so much, though.
Yeah, of course, no problem.
I guess I'll catch you on the flip side.
Right, I'll see
Or
you
I guess that's tomorrow.
Yeah.
Yeah. All right. Thank you so much.
Yeah, no
I didn't
problem.
realize that we'd kind of concluded up. Thank you so
Oh,
much.
no worries.